So today is the joint meeting of the AGORA program and also the last meeting of the regular Galaxy workshop. The idea is that a lot of the Galaxy simulation talks have been scheduled for today since they're relevant to both. Then the AGORA meeting continues over the weekend. So AGORA, is Javiera here? I don't see her yet. We had after the program started, we had a series of votes to choose the name, and Javiera is the one who suggested the name Assembling Galaxies of Resolved Anatomy with the acronym AGORA. And it seems that the natural way for English speakers to pronounce this is AGORA, but Javiera assures me that in Greek it's pronounced Agora. It's the meeting place in a Greek city-state.
Actually, look at the Merriam-Webster. It says Agora.
Right. So, so Javiera tells me, don't I know the final alpha is accented in Greek? And I checked with my wife, who's a scholar of Greek philosophy from the University of Chicago, and she says, of course, it's Agora. So I will pronounce it Agora, and you can pronounce it any way you like, except you'll face Javiera's wrath. So last year, Piero Madao and I called for people who are doing high-resolution galaxy simulations to meet here at the end of the Galaxy workshop last year. And many people did. The sort of leaders are the people whose names are in red on this slide, and several of whom are here in the audience. And there's now a total of about 90 people who signed up. We posted what we're calling the flagship paper a few days ago. Ji-Hun Kim is the person who's been largely responsible for organizing everything. Ji-Hun is here in the front row, and he's going to give the talk after this one. We were motivated to start the AGORA project partly by the Aquila project. This is the abstract of the Aquila paper. This was led by Cecilia Scannapieco. There were 13 different simulations, all done with the same initial conditions in that project. Let me see it. Yeah, I did turn on the microphone. They had the same initial conditions, but otherwise they used very different assumptions concerning virtually everything. Not just the subgrid physics, but also the large-scale physics, UV background, cooling, and so forth. There were large code-to-code variations in stellar mass, size, morphology, and gas content, but there were no successes. They were trying to simulate a Milky Way mass halo. It was one of the Aquarius halos, and they expected to make disk galaxies, and not a single one of their simulations produced anything that looked like any real galaxy. And the conclusion was that state-of-the-art simulations cannot yet uniquely predict the properties of the baryonic component of a galaxy, even when the assembly history of the host halo is fully specified. Developing feedback algorithms that can effectively regulate the mass of the galaxy without hindering the formation of high angular momentum stellar disks remains a challenge. There have been basically two responses to this. One response has been to actually try to solve the physics problems by going to high resolution. The other response has been to duck the issue and basically use a semi-analytic model technique, but applying it to simulations. Use a coarse resolution of a kiloparsec or 500 parsecs and fake everything else. Put in winds by basically dialing them in. Put in feedback by dialing it in. That's the approach of the Arepo simulations so far, and that's the approach also of the MAGIC simulations to a great extent. Those simulations are being run at typically 300 parsecs. Whoops. So the Aquila simulations typically had 500 parsec or worse softening. The best was 260 parsecs, which in co-moving coordinates at z of 9 is 26 physical parsecs. So that's very impressive, but then as you go down in redshift, it gets considerably worse. Since stars form in galactic disks, mostly, realistic simulations should resolve disks. The disk scale height of the Milky Way is about 100 parsecs. So furthermore, of course, stars form actually in giant molecular clouds with scales of tens of parsecs. So ideally, one would like to resolve those scales. The trouble is that doing that in a cosmological context with a scale of megaparsecs for the region that has to be done at high resolution is very daunting. And in fact, Phil Hopkins said yesterday that he'd run several simulations using the initial conditions that we recommend at 10 parsec resolution, but he left before we could find out how he did it, because that's kind of amazing. Well, anyway, these were the results, some of the results. This is the stellar mass halo mass relation, and the worst were Arepo and two of the Ramses simulations. They were the highest, nearly producing all of the gas reprocessing into stars. Typically what happens is that the stars form at very low radii and are rotating much too fast to be on the Tully-Fisher relation. This is the stellar circularities, so Jz divided by what you'd need to be in rotational support. And the typical situation is a lot of material with very low angular momentum, a sort of a super bulge, and a little itty-bitty disk. As you see, not one of the simulations in Aquila produced anything that looks realistic. Eros, on the other hand, looked very realistic. Eros was published in 2011, the original Eros. This paper came out in 2012. Eros was run at about 120 parsec gravitational softening, and the gas resolution was about 10 times better. So the Eros simulation was the first of these high-resolution simulations that produced a realistic disk. And now several other groups have succeeded in doing similar things with other codes. So this is the homepage of the AGORA project. You can go to agorasimulations.org, or that'll immediately take you to this, which is the actual site of this page. The AGORA project has the goals that are listed at the top, basically to prepare a series of simulations based on the same physics as well as the same initial conditions as much as possible. It's very timely. The music code by Tom Abel and Oliver Hahn is being used to generate initial conditions in every one of the simulation types, every one of the codes. The UV background model, the latest version of the Hart and Badow model, is being used by all the codes. The Grackle hydrocooling code has been developed, and it should be usable by all of the different codes. And the YT code, which was originally developed by Matt Turk as a kind of general analysis code for ENSO simulations, is very far along in being developed, being improved a lot, and being made into a code that can be used with output from any of these simulations. And I'll show you some pictures that were generated for all the simulations using the YT code. So the initial conditions are being generated by two different methods. The music method, which gives you self-consistent initial conditions. They've been run to guarantee that separation criteria that we agreed on last year are met, so that we have a more or less isolated halo but not unphysically isolated, with masses of 10 to the 10, 11, 12, and 13 solar masses, and for each case a busy merging history and a quiet merging history. And then in addition, a code that was originally developed by Volker Sprengel, the Make Galaxy code, or Make This code, was used by Oscar Agertz and Romain Tessier to generate initial conditions for roughly Milky Way size halo at redshift 1. So that, of course, the codes that are being used to run cosmological simulations are going to take a long time to get to redshift 1. And if people wanted to try their same code out and see how it does on a sort of redshift 1 galaxy. That's what people are being recommended to do. So this last year, a lot of effort has gone into developing all of the things I just mentioned. YT, we had YT developing meetings, including at Santa Cruz. Music has been improved, and these initial conditions have been generated largely by Jose Anorbe and especially Ji-Hoon Kim. The UV background, the cooling function. This is the cooling. These are some of the cooling curves that are being generated by the code, the Grackle code. And these are all described in the so-called flagship paper. Ji-Hoon Kim is the first author, and then everybody else in alphabetical order, which has just been put on the archive on Tuesday of this week. And this is a code that can run non-equilibrium cooling using the light elements that's appropriate for primordial nucleosynthesis output. So for the first stars calculations, if you're not doing that, then you can turn off this expensive part of the code and have a normal equilibrium cooling code, which is probably adequate for lower redshift. So as I said, YT is publicly available. It is still being improved, but it's, I think, the most capable general purpose analysis and visualization code that exists for analyzing galaxy simulations. We want people to store many time steps of the simulations so that they can be compared at basically the same physical times. And we need to have places where this can be stored. We have now a petabyte scale storage system for astrophysics here at UCSC to go with our new Hyades high performance computer, and also the San Diego Supercomputer Center and Alex Zale's Datascope program at Johns Hopkins will provide repositories where this kind of data can be loaded. We want to make all of this material publicly available on a short time scale, but initially the people who generate the outputs from the simulations will be the ones that control its publication, and together with the steering committee. And the idea is that we want to have the people have a chance to analyze their own code outputs in comparison with other groups and write the initial papers, but then we want to make everything available as quickly as possible. We've set up 4 working groups to develop the science tools, including YT and the initial conditions, and we have 10 working groups to develop the scientific results. James Wadsley remarked last year that if all we do is produce one paper like the Aquila paper, we'll have been a terrible failure. Instead, what we want is to have many papers, and in fact the goal of the whole project is to raise the entire level of high-resolution hydrosimulations of galaxies by improving our physical understanding, our understanding of why codes disagree and which codes seem to be doing the best physics, and also comparing to observations. So there are these many working groups. If you go to the website, you get all of this information. I'm not going to go through it now. This is the flagship paper, author list, and the abstract. So basically it says what I just told you. What I want to do in the roughly 10 minutes I have left is to talk. Wait, I'm supposed to get 20 minutes, right? Plus 5 minutes for discussion?
I have a stopwatch, Joel.
Okay, well, sorry, I'm looking at the clock that's on this thing. So very quickly, this shows the results of 9 of the simulation codes, starting from the same initial conditions. This is a relatively low resolution, pure dark matter simulation. They look similar. If you zoom in on the central regions, so this is roughly the virial radius of the halo at redshift 0. You'll see that they all look kind of different. And that's not unexpected. There's slight differences in timing, and but these are some of the examples, plus a full analysis of the radial distribution in the central halo and also the subhalo mass function. These are all in the flagship paper. The kinds of issues we want to address, including solving the general problem of too much star formation, especially at high redshift, producing as many bulgeless disk galaxies as observed, the effect of baryons on dwarf galaxies, the core cusp problem, and the too big to fail problem. Understanding the physical mechanisms that quench and preserve quenching in galaxies above a certain characteristic central density. The effects of different recipes on feedback and AGN, energy input, and probably we now really have to include the effects of asymptotic giant branch stars. And then finally, not finally, but just of the list that I have here, observations show that about half of all star-forming galaxies are at redshifts of 1 to 3 are clumpy. Do simulations see this? And what's the role of these clumps in forming spheroids? Most stars seem to form in disks, but today the vast majority of stars are in spheroids. So there seems to be a transformation process. And in running high-resolution simulation-based, like the Bolshoi simulation, based semi-analytic models, we and other groups, also on Millennium, have found that you cannot produce the number of spheroids that we see just based on major mergers, major wet mergers or major dry mergers for that matter. There has to be another process. And very likely the other process is disk instability, which Avishai calls violent disk instability. We use the Sunrise code, I won't have time to discuss it, to take the output from any of the AGORA simulations and compare them with observations. This shows how Sunrise reprocesses the blue that's without attenuation by dust into edge-on or face-on or any angle. This shows the effects of including dust. It spreads out the light as well as absorbing the light, because we do scattering as well as absorption and re-emission at longer wavelengths. This is some typical examples of running Sunrise on many different time steps of a given simulation. Of course, this is one of the roughly 90 simulations that Daniel Severino has run with resolutions now up to 15 parsecs, initially about 60 parsecs. When we process this, we generate images like the ones at the bottom, which include the convolving with the point spread function for the appropriate filter on Hubble Space Telescope, either the ACS filters in the optical band or the Wide Field Camera 3 filters in J and H band. We actually generate every band that HST can see, and then we also generate the far infrared self-consistently. And this is what these things would look like close up at 10 megaparsecs. But then we process them we also include noise, so that we can then compare them with observations. The effect of including dust is pretty profound. All the really brightest regions tend to be dust enshrouded, and they're not nearly as bright when you take the dust into account. We've started a project to compare in detail the Candel's observations and these simulated observations, and at the same redshifts and across the same masses. And these are some examples from Mark Mozina's dissertation. The observers classified 5,000 observed galaxies, 3,000 simulated galaxies by eye. At least 3 and usually 5 people independently classified them. And the Sursic measurements, this is from Galapagos, the system that was used on the observations, and also on the simulated galaxies. These show that the ones that are classified as smooth indeed tend to have high sursics. The ones that are classified as clumpy tend to have low sursics. This shows not clumpy and examples of clumpy galaxies. And the clumpy galaxies, the triangles here, tend to be above, in fact, exclusively are above a radius of 2 kiloparsecs. And above 3 kiloparsecs, they're mostly clumpy. And they tend to, as you see, have low sursics. Now that's the Candel's data. This is the simulated data. The simulations have a lower range in both radius and mass, and a smaller range in mass, but that's partly just because the simulations aren't completely representative. If you look at the general behavior of the clumpy versus not clumpy in the simulations and in the observations and in the other properties, they actually look really pretty similar. This is based on the Generation 1 and Generation 2 simulations by Daniel. The generation 3 with radiation pressure were not available when this process was started. Do these simulations produce this remarkable scheme where diffuse galaxies appear to become very compact galaxies? This is Guillermo Barrows' slide. As I mentioned, if you run the semi-analytic model, and I think people have shown this, and there'll be more discussion, I think Adia is going to mention this. We have a semi-analytic model developed by Lauren Porter based on Rachel Somerville's semi-analytic model. And what it does is it does produce this so-called fast track, where galaxies do quickly become more compact and then evolve into compact red nuggets, we call them, and then minor mergers tend to decrease the compactness, increase the size of these objects, in pretty good agreement with observations. So the question is, will simulations do this? The way we treat the disk instability in the semi-analytic model is just a guess. And it really should be based on better understanding, which will come, we hope, from these simulations. So that's my last slide, and I leave with the question, will the AGORA simulations agree with observations by these huge observing programs like CANDELS?
All right, thank you, Joel. All right, we have time for questions. Yes.
As you go, when you go down to smaller and smaller scales, you do see differences between the code. You said quite rightly that this is expected. So it is important as part of AGORA that we separate out what we expect to be sensible differences between codes simply due to the fact that it's a chaotic system. So basically, you can think of the code having an error bar. So if we start with very slightly different statistical realization of the initial field, then the code should agree as well as any individual code group itself when you make that small change.
Well, that's just really the dissipationless part, the dark matter part. I think everything you said is exactly what we expect. And to a great extent, I think it's true that the codes are now sufficiently mature that they will do that. And where they disagree, we'll understand why. For example, in low density regions, the adaptive mesh codes don't resolve that far. Where we're going to see much more important differences is in feedback and star formation, because that's all subgrid physics, and it'll be implemented in different ways in different codes. And there, the code comparison with theory, and the comparison with observations, I think is going to be very illuminating. One of the problems with these low-res simulations that mock up by basically adjusting things like the winds, the more or less proper, observed behavior of galaxies. Those simulations tend not to have these very clumpy galaxies that are ubiquitous in the observations in star-forming galaxies that are not too small. And that process, this clumpy process, may very well be a very important process that drives the formation of compact spheroids. And so the question is, are the codes going to see processes like that?
Question.
How are you going to make the purgeless these galaxies? Since I would expect that the feedback would have to take place outside of the galaxy rather than inside, because we need to have gas only to make it fit.
The question, I think, is not how do we, in the simulations, make bulgeless galaxies, but how the universe makes bulgeless galaxies. And that's, I think, a really important question. And we're going to have to see.
Feedback only inside the galaxies, or are you investigating mechanisms that could take place, like a better treatment of the intergalactic medium?
Every one of these things is going to be part of the investigation. I mean, the idea is that you have to have a high-resolution region that will encompass everything that could possibly interact with the galaxy.
It was said like 2 days ago that that doesn't mean that you're going to have high resolution in the IGM, which is not supposed to be the place where you have the high resolution.
Well, our plan is to have high resolution in roughly a megaparsec scale region, at least, and then lower resolution around that, so that everything that can directly affect the galaxy that's forming in the center will be resolved, at least as well as the code can do.
All right, one more quick question. Anyone? All right, if not, let's thank Joel again.